Clustering is one of those topics that sounds simple on the surface because it is often described as grouping similar things together, yet it becomes surprisingly subtle as soon as you ask what similar really means. In a beginner setting, clustering is appealing because you do not need labels, and it feels like the model is discovering structure on its own. In real data work, especially in environments that involve security signals and operational data, that label-free nature is both a strength and a trap. It is a strength because labels can be expensive, inconsistent, or unavailable, and clustering can still provide a useful map of what is common versus unusual. It is a trap because clusters can look meaningful even when they are artifacts of scaling, measurement choices, or the shape of the algorithm. The goal is to learn how to use clustering as a careful exploratory tool rather than as a shortcut to conclusions you cannot justify. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A good way to ground clustering is to separate the task of finding groups from the task of interpreting what those groups mean. Clustering algorithms will always produce some structure because they are designed to partition or organize points, even when the data has no real natural groupings. The algorithm cannot tell you whether the resulting groups correspond to meaningful categories like types of users or kinds of activity, and it certainly cannot tell you whether a cluster is safe or risky. That interpretation requires context, sanity checks, and comparison to known patterns. In security-related datasets, clustering is often used to group similar sessions, devices, or events so that analysts can prioritize investigation or understand common behavior patterns. The immediate beginner misunderstanding is to treat clusters as truths, like a cluster equals a real category, when a cluster is only a model-produced grouping under a chosen definition of distance and similarity. Thoughtful clustering means you remain aware that you are building a lens, not discovering a law of nature. K-means is often the first clustering method people learn because its logic is intuitive, but you should understand its assumptions so you can predict its limits. K-means tries to place k-centroids, which are representative points, so that each data point is assigned to the nearest centroid, and the total within cluster squared distance is minimized. In plain terms, it is trying to make clusters that are compact and roundish in the feature space defined by your inputs. That compactness assumption is the key limitation because many real groupings are not round, not equal in size, and not separated cleanly. K-means also forces every point into some cluster, which can be uncomfortable when you know some points are simply outliers or noise. Beginners sometimes think K-means will discover the right number of groups automatically, but it will not, because K is an input choice. Understanding what K-means is optimizing helps you understand when it can mislead you. Scaling consequences are especially sharp for K-means because the distance measure is usually based on Euclidean distance, which is dominated by features with large numeric ranges. If one feature represents bytes transferred and another represents a small ratio, the bytes feature can overpower the clustering, and you end up grouping points by volume rather than by behavior. Even when you scale properly, the presence of correlated features can still distort clustering because the algorithm treats each dimension as contributing separately to distance. This is one reason clustering is not just about picking an algorithm, but about representing the problem in a way that makes similarity meaningful. In security monitoring, a cluster that forms purely on time of day might be a real pattern, but it might also be an artifact of how logging is done, such as batch jobs running nightly. If you are not careful, you will mistake schedule structure for behavioral structure. Thoughtful clustering includes asking whether the features you chose reflect stable characteristics or accidental operational rhythms. The cluster output can only be as sensible as the space you built for it. Choosing K is another place where beginners can accidentally turn clustering into a guessing game. So it helps to think about what K represents. K is not a magical answer. It is a resolution setting that determines how finely you slice the data into groups. A small K gives you broad groupings that can summarize major modes of behavior, while a large K gives you more granular groupings that may capture subtypes or may simply fragment the data. When you increase K, the within-cluster distances will usually shrink, which can create the illusion of improvement even when the new clusters are not meaningful. A thoughtful approach is to connect K to your purpose, such as whether you want a few understandable behavior profiles or whether you want many microgroups for routing and triage. In security workflows, too many clusters can be hard to use because nobody can interpret them, and too few clusters can hide important differences. The right K is often the one that produces stable, interpretable groupings that support a decision, not the one that produces the smallest distances. K-means also has known sensitivity to initialization, which is a polite way of saying it can give you different results depending on where it starts. Because the algorithm iterates by assigning points to centroids and then moving centroids to the average of assigned points, it can settle into different local solutions. That means two runs with the same data can produce different cluster assignments, especially when clusters overlap or when the dataset has ambiguous boundaries. For beginners, this is an important lesson about stability because you should not treat one clustering run as a definitive answer. In practice, you often look for cluster structures that repeat across multiple runs or that remain similar under small data changes. In security settings, unstable clusters can cause operational confusion because a session might switch clusters from day to day even if behavior has not changed meaningfully. Thoughtful clustering favors consistency and interpretability over fragile precision. When a clustering method is highly sensitive, it is a signal to adjust features, consider a different method, or accept that the data may not have strong cluster structure. Another key limitation of K-means is how it handles outliers, because outliers can drag centroids and distort cluster shapes. Since centroids are means, a single extreme point can shift the centroid location, which then changes assignments for many other points. This is especially problematic when outliers are common, as they often are in operational datasets that include rare errors, bursts of activity, or unusual but benign workflows. K-means also tends to prefer clusters of similar size because of the way it minimizes squared distances, which means it can split a large natural group into multiple clusters while merging two smaller distinct groups. In security analytics, you might see a large cluster of normal behavior and a small cluster of suspicious behavior, and K-means may not respect that imbalance unless the feature space makes the suspicious behavior clearly separable. Beginners sometimes interpret this as the algorithm failing, but it is the algorithm doing exactly what it was designed to do under its objective. Thoughtful use means you do not ask a method to solve a problem it is not built to solve. This is where density-based methods become useful, because they are designed around a different definition of what a cluster is. Instead of assuming clusters are compact balls around centroids, density methods treat clusters as regions where points are packed closely together, separated by regions of lower point density. This allows them to discover clusters with irregular shapes, like long curves, rings, or blob-and-tail structures that K-means would struggle to represent. Another major benefit is that density methods can naturally label some points as noise, meaning they do not belong to any dense region, which is often a better match to reality than forcing every point into a group. In security contexts, this noise labeling can align well with the idea that most activity fits typical patterns while some activity is sparse, rare, or anomalous. The beginner misunderstanding here is to think density methods are always better when they are simply better for certain geometries. They can struggle when densities vary across clusters or when parameters are chosen poorly. Density-based clustering often depends on parameters that define how close points must be to be considered neighbors and how many neighbors are needed to form a dense region. The conceptual risk is that these parameters can quietly encode your definition of what counts as a meaningful group, and small parameter changes can shift cluster assignments. If the neighborhood radius is too small, the method may fragment clusters and label many points as noise. If it is too large, it may merge distinct groups into one sprawling cluster. In datasets where one cluster is very dense and another is more spread out, a single density threshold may not fit both well, which can cause the method to either miss the spread-out cluster or overmerge everything around it. In security data, this density variation is common because some user populations are very consistent while others are more diverse. Thoughtful clustering means you expect parameter sensitivity and you treat the resulting clusters as hypotheses that need validation. The method's flexibility is valuable, but it also means you must be disciplined about how you interpret results. Evaluation is the part of clustering that many beginners skip, partly because there is no single right answer without labels. Still, you can evaluate clustering thoughtfully by combining internal measures, stability checks, and usefulness tests. Internal measures look at properties like how compact clusters are and how separated they are, which can provide a rough sense of quality under the algorithm's notion of distance. However, internal measures can favor certain shapes, and they can reward overfragmentation, so they should not be treated as final proof. Stability checks ask whether clusters persist under resampling, small perturbations, or different random starts, which helps you detect fragile patterns. Usefulness tests ask whether the clusters support your goal, such as whether they separate common from uncommon behavior in a way that an analyst can act on. In security workflows, a useful cluster is often one that reduces cognitive load, helps route cases, or surfaces a small set of unusual groups for review. Thoughtful evaluation includes asking whether the clusters make decisions easier, not just whether they look mathematically tidy. It also helps to recognize that clustering outputs can be misleading when data has gradients rather than true groups. Some datasets do not have distinct clusters. They have continuous variation where behavior slowly changes across a spectrum. In those cases, forcing clusters can create artificial boundaries that suggest categories that do not exist. K-means will still cut the spectrum into K parts, and density methods may produce clusters where density happens to be higher, but the underlying reality might be continuous. In security terms, user behavior often changes gradually with role, experience, and workload, and you may see a continuum rather than distinct classes. A beginner might look at cluster labels and assume the clusters represent discrete user types, when the model is just slicing a gradient. Recognizing this possibility protects you from overinterpreting and from building policies around arbitrary boundaries. Thoughtful clustering includes checking whether cluster boundaries align with real discontinuities or whether they cut through a smooth distribution. If the world is continuous, your interpretation should reflect that continuity. Another practical issue is that clustering can reflect data collection artifacts more strongly than the underlying behavior you care about. If one set of records comes from a different logging source, a different parser, or a different environment, the features may shift in ways that cause clustering to group by source rather than by behavior. This can be especially common in cloud datasets where services emit logs with different fields, different frequencies, and different semantics. A cluster might simply represent a class of events from a particular subsystem, which could still be useful, but it is not the same as discovering behavioral groups. The safe approach is to test whether clusters align with known nuisance variables, such as region, logging pipeline, or time window. If they do, you have learned something about your data pipeline, not necessarily about security risk. That is not a failure, but you should describe it accurately and avoid implying the clustering discovered attacker tactics. Thoughtful clustering includes humility about what the algorithm can see and what it cannot. When you communicate clustering results, it is important to phrase claims in a way that reflects uncertainty and avoids turning clusters into labels that sound like diagnoses. Cluster identifiers are conveniences, not ground truth categories, and they can change if you change features, parameters, or sampling. In practice, you often name clusters based on observed characteristics, like high-volume file activity or frequent authentication events, but those names are interpretations, not facts produced by the model. In a security setting, that distinction matters because calling a cluster suspicious can lead to unnecessary escalation, while calling a cluster normal can lead to blind spots. A better communication pattern is to describe what is common within the cluster, what distinguishes it from others, and what open questions remain. You can also emphasize that clustering is an exploratory step that can guide labeling, policy refinement, or deeper supervised modeling later. Thoughtful clustering communication treats clusters as a map that helps you navigate data, not as a verdict about what the data means. This keeps stakeholder expectations aligned with what the method can honestly deliver. The most useful way to think about clustering for the CompTIA Data AI certification is as a disciplined process of choosing a similarity definition, selecting a method whose assumptions match the data geometry, and evaluating results in a way that respects the lack of labels. K-means is a strong, simple tool when clusters are roughly compact and when you have scaled features appropriately. But it can mislead when shapes are irregular, when outliers are common, or when cluster sizes vary widely. Density methods can discover irregular shapes and can label noise, which often matches real operational data better. But they require careful parameter thinking and can struggle when densities vary. Evaluation is not optional, even without labels, because you can still test compactness, separation, stability, and practical usefulness. When you apply clustering thoughtfully, you avoid the trap of treating clusters as truth and instead use them as structured evidence that guides better questions. That mindset is what turns clustering from a colorful chart into a reliable part of a real analytic workflow.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.